Module 6 covers firefighting strategies and foam use tactics for controlling and fighting fires associated with the flammable liquid hazards of ethanol blended fuels.
Next up, we have Module 6, in which we'll be discussing firefighting foam principles. We would like you to be able to describe the manner in which foam applications can be used to fight fuel fires, to list the ways in which foam applications suppress fire, to predict when to fight fuel fires and when to simply protect surrounding areas, and to state generally accepted rule of thumb for the use of foam applications on ethanol blended fuel fires.
As discussed previously, we have seen the production of ethanol is quite large and likely to continue to increase. As always, emergency responders should be ready for emergencies associated with flammable liquids. Ethanol blended fuels are similar to other flammable liquids and their hazards. The predominant danger from ethanol emergencies is not from the incidents involving cars and trucks running on ethanol blended fuel, but instead from cargo tank trucks and rail tank cars carrying large amounts of ethanol, manufacturing facilities, and storage facilities. Responders need to be prepared for large-scale emergencies and prepared with the most effective techniques and extinguishing media. This module will focus on foam basics and then foam applied specifically to ethanol-related emergencies.
The technical definition of what is foam is found in NFPA 11. Foam concentrate is the concentrated product of which we're going to make foam. Alcohol-resistant foam concentrate is a concentrate used for fighting fires on water-soluble materials. So when your chemical that you're dealing with, the product that you're dealing with is a polar solvent that mixes with water, the responder has to use foam that's compatible with that, or alcohol-resistant AFFF.
Ethanol will continue to burn at 5 parts water to 1 part ethanol, or a 5-to-1 ratio, or 500% dilution. Many extinguishing agents are effective on flammable liquids. However, foam is the only agent capable of suppressing vapors and providing visible proof of security. Reasons to use foam include a foam blanket on an unignited spill can prevent a fire. The suppression of vapors prevents them from finding an ignition source. Foam can provide post-fire security by protecting the hazard until it can be secured or removed. Finally, foam can provide protection from flammable liquids for fire and rescue personnel during emergency operations. How foam works. Foam can control and extinguish flammable liquid fires in a number of ways. Foam can exclude oxygen from the fuel vapors and thus prevent a flammable mixture, cool the fuel surface with the water content of the foam, prevent the release of flammable vapors from the fuel surface, and in some environmental forms, emulsify the fuel. Foam tetrahedron. Foams used today are primarily of the mechanical type. This means that before being used, they must be proportioned, mixed with water, and aerated, mixed with air. 4 elements are necessary to produce a quality foam blanket. These elements include foam concentrate, water, air, and aeration. All of these elements must be combined properly to produce a quality foam blanket. If any of these elements are missing or are not properly proportioned, the result is a poor quality foam or no foam at all.
Ethanol, when it's burning, is a Class B fire. Foam is effective on Class B fires. Foam will extinguish a Class B fire by suppressing the vapors and cooling the product at the same time. There are two different types of Class B products: simple hydrocarbons, oil, gasoline, diesel fuel, and then polar solvents, anything that includes ethanol or ethanol blended fuels.
Foam terminology. Before discussing the types of foam and the foam making process, it is important to understand the following terms. Foam concentrate is the liquid substance purchased from a manufacturer in a container, pail, drum, or tote. Foam solution is the mixture obtained when foam concentrate is proportioned, mixed with water prior to the addition of air. Finished foam is obtained by adding air to foam solution through either entrainment or mechanical agitation. Types of foam. Several foam types have been developed over the years, each with particular qualities. Protein foam, one of the earliest foams, is produced by the hydrolysis of protein material such as animal hoof and horn. Stabilizers and inhibitors are added to prevent corrosion, resist bacterial decomposition, and control viscosity. Fluoroprotein foams are formed by the addition to protein foam of special fluorochemical surfactants that reduce the surface tension of the protein-based concentrate and allow more fluid movement. Aqueous film-forming foam, AFFF, replaces protein-based foams with synthetic foaming agents added to fluorochemical surfactants. Designed for rapid knockdown, AFFFs sacrifice heat resistance and long-term stability. Film-forming fluoroprotein foam, or FFP, is a protein-based foam with the more advanced fluorochemical surfactants of AFFF. FFPs combine the burn-back resistance of fluoroprotein foam with the knockdown power of AFFF. Alcohol-resistant AR foam is a combination of synthetic stabilizers, foaming agents, fluorochemicals, and synthetic polymers designed for use on polar solvents. The chemical makeup of these foams prevents the polar solvents from destroying them. Today's more modern AR foams can be used on both polar solvents and hydrocarbons. Foam will remove heat at a faster rate than it is released. Separate the fuel from the oxidizing agent. Dilute the vapor phase concentration of the fuel and/or oxidizing agent below that necessary for combustion, and terminate the chemical chain reaction sequence.
AFFF types of foam lowers the surface tension, will rapidly spread across the surface, and has a high burn back resistance and a quick knockdown. However, when we apply AFFF to polar solvents, the polar solvent will tend to destroy that fine film blanket. And so in order to deal with that, manufacturers have come out with alcohol-resistant AFFF, which will resist the product from actually eating the film blanket. So why use alcohol-resistant foam? Alcohol-resistant foam is the only agent capable of suppressing vapors on a polar solvent. The foam blanket on an unignited spill can prevent the production of vapors, and the suppression of those vapors prevents a fire from igniting or reigniting. Alcohol-resistant foam provides protection from flammable liquids for fire and rescue personnel during emergency operations. This chart shows you the different types of foam and how they judge their effectiveness. Effectiveness is judged on how quickly it knocks down the fire, how resistant it is to the heat of that fire, the tolerance it has to the fuel or the product that is spilt or on fire, its ability to suppress and maintain suppression of vapors, and then finally its tolerance to alcohol. Alcohol-resistant foams are the only types of foam that can give us protection in all 5 of these areas. In order to produce foam, you have to have appliances. You have to have a method of proportioning the foam concentrate into the water. Foam concentrate, if we're using alcohol-resistant AFFF, that alcohol-resistant foam can actually be used in different concentrations based on the fact that we're dealing with either a pure hydrocarbon or a potential polar solvent. So in the different concentrations, we will need a proportioner capable of adjusting those concentrations. So when we're talking about 3-6% foam, we can use it in the 3% mode for a typical hydrocarbon, but we have to bump it up to the 6% mode when we're dealing with polar solvents. Foam proportioning systems include eductors, which can either be inline or already pre-plumbed into a vehicle. Some foam proportioning systems can also have a bypass type of eductor. And this means you can switch from applying foam in concentrate to going back to flowing just water. But remember, if you begin to apply water to your foam blanket, you will deteriorate that foam blanket. So you have to be very, very careful when you're using these types of eductors. In order to appropriately apply the foam, we need a nozzle. And the nozzle needs to be of the aeration type that will add air into the system so that it can be applied appropriately. Some foam nozzle systems include the eductor right at the nozzle.
This image shows a fire hydrant with a foam nozzle attached to it. Air aspirating nozzles. Air aspirating nozzles are foam-generating nozzles that mix air and atmospheric pressure with foam solution. See Figure 6.6 in the participant guide. These nozzles produce an expansion ratio of between 8:1 and 10:1 and produce a good quality, low expansion foam. Non-air aspirating nozzles. Fog nozzles are an example of non-air aspirating nozzles. See Figure 6.7 in the participant guide. Non-air aspirating nozzles produce an expansion ratio of between 3:1 and 5:1. This expansion ratio is not as good as that of air aspirating nozzles, but these nozzles often add some versatility which can be beneficial in various fire attack situations. Versatility includes the ability to switch from a foam solution to water in order to protect personnel and provide area cooling. Air aspirating nozzles do not offer this advantage. A disadvantage of aspirating and non-air aspirating nozzles is that you must have additional equipment in order to generate foam. In addition, the gallonage setting on the nozzle must match the set flow for the eductor. It is important to understand the benefits of both types of nozzles in order to select the most appropriate one.
Large-scale foam appliances. So here you can see a picture of a trailer. This trailer specifically has a 1,000 gallon per minute foam application nozzle on it. With this, instead of dealing with 5-gallon buckets or pails of foam, we're actually dealing with totes of foam. So a tote of foam can be close to 400 gallons of foam. Many departments, many facilities are going to have access to a foam trailer. Very large scale foam application nozzles. So now we're looking at something capable of 4,000 gallons per minute. You're going to need a system like this if you have a large storage tank on fire. Proper application of foam is critical. The key to foam application is to apply the foam as gently as possible to minimize agitation of the fuel and the creation of additional vapors. The most important thing to remember is never plunge the foam directly into the fuel. The bounce-off method is effective if there is an object in or behind the spill area. The foam stream can be directed at the object, which will break the force of the stream, allowing the foam to gently flow onto the fuel surface. The bank-in method. When no obstacles exist to bounce the foam off, firefighters should attempt to roll the foam onto the fire by hitting the ground in front of the fire. The foam will pile up and roll into the spill area. This technique is particularly effective with non-air aspirating fog nozzles. The mechanical agitation of the foam hitting the ground will help to aerate the foam. The rain down method. An alternative application technique is to rain down the product. The nozzle is elevated and the foam is allowed to fall over the spill as gently as possible. Remember, never plunge a stream of foam directly into the fuel.
Some of the foams mentioned in the previous sections have been around for over 50 years and have proven to be very effective on hydrocarbon fuels. However, these foams were not developed for application on ethanol blended fuels and are simply ineffective. This is because the alcohol or ethanol content of the blended fuel literally attacks the foam solution, absorbing the foam solution into the ethanol blended fuel. Foam that is designed to be alcohol resistant forms a non-permeable membrane between the foam blanket and the alcohol type fuel. It is crucial that these AR foams are used in combating ethanol blended fuel fires, including E10. This is an important point. Additionally, to be effective, these foams must be applied gently to the surface of the alcohol or ethanol blended fuels. Otherwise, the foam is absorbed into the fuel and will not resurface to form an encapsulating blanket. Extensive testing done at the Ansel Fire Technology Center indicated that even at low-level blends of ethanol with gasoline, as low as E10, there is a major effect on foam performance. The testing also indicated that with high-level blends of ethanol with gasoline, even AR foams required careful application methodology and techniques to control fires.
Alcohol-resistant foams. AR-type foams must be applied to ethanol fires using Type 2 gentle application techniques. For responding emergency services, this will mean directing the foam stream onto a vertical surface and allowing it to run down onto the fuel. Direct application to the fuel surface will likely be ineffective unless the fuel depth is fairly shallow, less than 1/4 of an inch. Type 3 applications using fixed and handline nozzle application is prone to failure in ethanol blended fuels of any substantial depth. The only time it is effective is when deflected off of surfaces such as tank walls to create a gentle style application. It has also been found that even with indirect application off surfaces, it may require substantial increases in flow rate to accomplish extinguishments. Therefore, in situations where AR foam cannot be applied indirectly by deflection of the foam off tank walls or other surfaces, or there is no built-in application device to provide gentle application, the best option might be to protect surrounding exposures. Foam application rates. The information that we're going to cover in the next few slides comes right out of NFPA 11, which is our standard on applying foam. AFFF type foams require approximately 1 gallon per minute of foam solution flow for every 10 square foot of burning surfaces of a hydrocarbon type fuel. Ethanol blended fuels require approximately double that flow or 2 gallons per minute per 10 square feet of an AR type of foam solution. As with all types of foam, mixing percentages is dependent upon the type and the design of the foam concentrate. What NFPA is telling you is that for every 10 square foot of a flammable liquid fire that is involving a typical hydrocarbon, you need to be able to apply 1 gallon per minute of the foam solution to that area in order to put it out. In a polar solvent such as ethanol, NFPA recommends the firefighters double that concentration, or 2 gallons per minute per 10 square foot of fire area. Departments that are subject to incidents involving the various blends of fuels found on highway incidents or at storage facilities should strongly consider converting to AR foam concentrates, or develop a means of having a cache of AR foam readily available. When purchasing foam, ensure that it is UL certified in order to remain compliant with NFPA standards. Significant amounts of AR foam may be required. If your emergency response plan involves relying on mutual aid and mutual aid assets, be sure to confirm what type of aid will be provided and what firefighting resources are available. The mixing of different brands of foam can potentially hinder the desired outcome and efficiency in which to be performed. It is imperative that departments verify the compatibility of foams with their mutual aid providers. Also, be sure to train emergency responders to use these assets. Many departments will utilize the local airport to come out with a crash truck to provide foam for an incident. Make sure that airport either is using AR AFFF or is capable of dealing with polar solvents. Many of them won't be. Keep in mind that alcohol-resistant foams are effective on both alcohol and hydrocarbon fires. AR foams have a special polymer that forms a protective membrane between the fuel and the foam as it contacts the polar fuel, making fire extinguishment possible. AR foams also make the foam more stable and heat tolerant, resulting in better burn back protection or resistance when compared to conventional foams. As a matter of fact, some of the AR foams have quicker knockdown abilities and longer foam retention times than some of the traditional protein-based hydrocarbon foams. It is recommended that a thermal imaging camera be used to more accurately determine if a fire is completely extinguished, especially during sunlight hours. Also note, foam tanks and totes cannot be shaken and remixed easily and can stratify. To avoid this, it is recommended that a maintenance program be in place to re-agitate the foam periodically. If a department has specific hazard that only involves non-alcohol or non-ethanol blended fuels, they may want to consider non-AR foam for that specific hazard. However, for transportation incidents, they should have AR foam readily available. If you're not taking your foam concentrate for a ride every now and then, it won't stay good. It'll coagulate inside its containers. Proper scene evaluation will assist in making the right choices for a successful incident mitigation. Keep in mind that AR foams are effective on both alcohol fires and hydrocarbon fires. If upon arriving on the scene of an emergency, if you're having difficulty identifying the exact contents of a tanker, then you always want to apply the foam at the higher rate or as if it was a polar solvent. If you're applying it as a polar solvent and it ends up being strictly a hydrocarbon, it will not hurt. It'll still be advantageous to you. But if you apply it at the lesser rate and it does end up being a polar solvent, you will not get the desired results from the foam. Application rates recommended for ethanol spill fires of a shallow depth follow NFPA 11. Increasing the foam application rate over the minimal recommendation will generally reduce the time required for extinguishment. NFPA recommended application rate for film forming types of foam equals 1/10 of a gallon per minute per square foot, or 1 gallon per 10 square foot for a period of time of 15 minutes. In an ethanol or a polar solvent fire, they recommend increasing that to 0.2 gallons per minute per square foot, or 2 gallons per minute for 10 square foot of fire. To determine the amount of foam concentrate required, you must find out the type of fuel and the area of involvement. The square footage multiplied by the application rate will give you the recommended gallons per minute. The whole formula will give the concentrate total. This includes the time duration for the attack and percentage rate for the concentrate to be used. As a note, double the amount of foam concentrate on hand prior to initiating fire attack. This will cover the fire and maintain the foam blanket following the knockdown. Time duration depends upon the nature of the incident. Typical times are 60 minutes for tanks and 20 minutes for ground spills.
Examples of application rates for hydrocarbons. An area of 2,000 square feet of regular gasoline is burning. You have Universal Plus 3-6% foam available for securing the flame. At 0.10 gallons per minute per square foot times 2,000 square foot, that equals 200 gallons per minute of foam solution required. At 3/100ths times 200 gallons per minute, that would equal 6 gallons of 3% concentrate required per minute. 6 gallons times 15 minutes equals 90 gallons of 3% AFFF concentrate required to control, extinguish, and initially secure a 2,000 square foot hydrocarbon fire. Application rate calculations tell you more than just how much foam do I need. They also tell you what hardware is required for a given size fire.
NFPA also shows a number of application rates based on what we are dealing with. If it's a simple hydrocarbon tank, depending upon its size, the flow rates and the concentration changes. The length of time. In a large storage tank, they are anticipating that those flow rates must be maintained for sometimes up to a full hour in order to fully extinguish the fire in the tank. Incident foam needs, rule of thumb is to double the amount of foam concentrate on hand prior to initial fire attack. AFFF foam turned out to be the best choice for incidents involving those types of fuel. Because AFFF foam works well on gasoline fires, it is the recommended choice for all fuel fires involving either gasoline or ethanol blended fuels. If it is unclear the chemical nature of the burning fuel, AFFF is the preferred choice from a response standpoint. Refer to the foam manufacturer for the recommended application rate. Whenever you're dealing with a rail car that's on fire involving ethanol or any flammable liquid, remember you need to cool the metal of that rail car before attempting to extinguish the fire with foam.